Silicon carbide is stirring up the market for power electronics, specifically in the traction inverters at the heart of electric vehicles. Silicon carbide MOSFETs have faster switching speeds, higher breakdown voltages, and other high-end characteristics compared to silicon IGBTs. But they are still relatively new and experiencing some growing pains. And as a result, they tend to be more expensive than silicon when packaged into power modules. Infineon is trying to minimize the drawbacks of both technologies. It recently released what it calls the first fusion power module that combines silicon carbide MOSFETs with silicon IGBTs all in a single module. So I think it makes sense to maybe start with silicon carbide, which is becoming a bigger and bigger topic as it relates to the electric vehicles and specifically the traction inverters. So I'm just wondering if you can start out by going into why this transition is happening and sort of some of the technical differences compared to silicon.
So thanks for asking this question, and I would like to start with giving you some numbers on here. So in 2013, if you look on the BEV, the battery electrical vehicle, the bill of material most likely will range about like $2,000 per car. And that's a massive amount of, let's say, semiconductors. Also some numbers is like in 5 years from now on, is also every second car will be electrified. And also, if you have a look, also 5 years from today, the XEV market, the SiC market, in drivetrain, the power, will reach nearly 55%. So it's a dramatically increase of the SiC, and also on the same stage, so silicon, as we call it, CSE, will go down to 45%. So this is like an estimation. So the SiC market will increase, and the silicon carbide is, or the SiC is kind of a semiconductor material that has really been gaining significant attention within the electrical vehicle market, so the EV market. And as you also pointed out, particularly in the field of the power electronics, also the traction inverters. And in recent years, the SiC has been increasingly also replacing the traditional, the silicon, also in not only traction inverters, also in various EV applications. And this is also for good reasons, right? So the one of the primary drivers behind of the adoption of the SiC in EVs is the perfect, the superior performance characteristic compared to the silicon of SiC. Because of SiC has, first of all, a higher thermal conductivity, so which enables SiC to operate at higher temperatures and frequencies, in making it more efficient and more reliable. And also, this is also the one of the top performance of the SiC, of the silicon carbide. It has a higher breakdown voltage, which also allows to handle higher power densities and reduce the risk of the electrical failures. So therefore, in the complete EV market, which is rising, the SiC is just being used to replace silicon in several applications in the power electronic, but it also comes with a higher price tag. So there's always like the second part of the coin, right?
So I was wondering if you could talk at all about what is driving the fact that the price tag is higher. Is it just challenges around manufacturing silicon carbide specifically, or is it just economies of scale? You know, silicon has been around for such a long time that semiconductor companies are very good at manufacturing it in very large quantities. Is it just an economics question, or is it a manufacturing issue as well?
So Infineon is really good, and this is also driving Infineon in both technologies, also in the silicon, so in the IGBTs, as we call it, and also in the silicon carbide. So we can do both. This is one of the major drivers also for us, to have the possibility and also to lever both technologies and to use also both technologies for us within the products. And as I'm coming from I'm responsible for the high voltage, the modules. So particularly also for a new product, the fusion. That's exactly why we're using those both technologies into one product, having a look into, right?
So as you noted a couple of times, Infineon recently introduced what it's calling a fusion power module that covers for some of the drawbacks of silicon and the drawbacks of silicon carbide by combining them both. So can you sort of take us inside the new module and just sort of walk us through what's inside of it?
James, absolutely. So let me share some insights. So where's that fusion coming from? Where's the motivation coming from? So basically, the EV applications, if you have a look on the WLTP drive cycle, so this is basically the applications are often driven in the light load conditions in this cycle. And we have discovered this in this light load discussion at the condition, 30% of, let's say, of a SiC chip content would be sufficient for driving this in the common operating conditions. It also means in the high load currents, which is usually supported by IGBT in the diode, it's driven not that common. So means basically, so the basic principle of that would be light load, we are using the SiC. In the full load, we're using the silicon. This is the motivation, the idea behind of using, let's say, two different technologies in one module. So it's the magic behind as we call it, the hybrid pack drive fusion is all about finding the sweet spot between the performance and then because we also talked about before the drawback on the SiC, the performance and the cost. This new module, the system suppliers, they can get almost the same efficiency as a full SiC solution, as a full silicon carbide solution. But the beauty is only with 30% SiC content and 70% silicon area. And this is basically a huge win. To be real, so a full SiC module can offer a higher efficiency, but again, it comes with a, let's say, a hefty price tag on that. And this is exactly why the hybrid pack drive fusion steps into and comes into here. So this is the, let's say, the perfect compromise on that. So the combination of a cost efficiency IGBT with SiC components, then you get the best of both worlds, right?
So can you maybe discuss some more technical details of the module? Maybe how many of each power transistor you're using and how they're arranged, and any other details you can shed some light on there.
Sure. Not quite sure it's a podcast, but we also video, and I've also brought that module with me, right? This is, as you can see, it's a hybrid pack drive module from Infineon. So the same package, and we're basically using a toolkit which is pretty much existing. So from back end, as we call it, packaging, and also from front end, there's the dice, and then really smartly putting everything together. This is, as we call it, like the fusion, merging different technologies together to one really new product. And so what makes the tick? In the end, it's the perfect switching harmonization between our front-end technology, the EDT3, and SiC generation 2. So this is optimized for the performance and efficiency. And also, it comes also with the charm of you can drive it with a single gate driver capability. So it's a breeze to integrate into designs for the OEMs and the tier ones. we are using the Infineon's latest die-attach technology with sintering and pairing those EDT3, IGBT, and SiC generation 2 technologies together. If you're asking for technical details, so it's got a short circuit robustness of currently 1.5 microseconds, and we can handle with the product which is now coming up to the market by planning end of 25 with up to 750 amps. So that means if you calculate that, we can future it up roughly up to 220 kilowatt, and ensuring a high reliability over the entire temperature range. So from -40 to +175 degree. It also has the possibility to integrate Hall sensors in the package, because it's a well-known package for the phase current measurement in a power module. And this is also very good for, let's say, for the cross-selling, as you can also use like our Swoboda sensors on here in Hyperpack Drive Generation 2 Fusion. You can put a single gate driver from Infineon also on here, which is also basically used for standard SiC applications. So for example, the EDI 3035 AS or the EDI 3040 AS. So this you can easily use, but also for the choice for the customers, dual gate driver would also be possible for this module. So this is kind of giving you the details on this module.
Okay, so you mentioned a few times that the fusion module can get close to the same efficiency as a full silicon carbide module, but with around 30% silicon carbide instead of the
Right,
full
right.
amount. Can you maybe go into how Infineon accomplished that, considering it seems like surprising that you'd be able to get close to the same efficiency with only around a third of the silicon carbide?
Yeah, it's not the same efficiency. So again, so silicon carbide still would be the right choice for gaining 100% efficiency. But to come with only 30% on a SiC chip content, we might reach up to 70, 75% efficiency. And that's I would say the game changing, because there the drawback of the cost of the SiC is not that significant. So it's still there, but not as significant as you can there use in the application the IGBT. And what's making the magic behind that is the perfect switching harmonization of our front-end technologies, so IGBT and SiC, because we are using the EDT3 technology and also the SiC generation 2 technologies, and they have really switching behavior which is really fast, really similar fast. And this is exactly why the fusion works together in this context, right?
That's interesting. I have read some research about sort of scaling up this type of technology into a sort of hybrid or fusion inverter. And one of the challenges that constantly comes up is the fact that the IGBTs that are used and the silicon carbide MOSFETs that are used have different switching frequencies, because you want to take advantage of the high frequency of the silicon carbide. But that creates some complications when it comes to controlling them, because you have two different switching speed devices that are in the same circuit. So it's interesting that you're sort of making sure that both are switching around the same rate to get around that.
So this is, I would say, the concept of a fusion is not very new, right? Because this was also done, if you go back 30 years research, they were already being used SiC and silicon, if you look on the diodes and switches on the IGBT, but not on the switches itself. So therefore, this is the first module on the market where we have the magic combination on the switches, on the SiC and the IGBT switches. And coming back to your question of how to control it. So the Hyperpack Tri-Fusion is optimized for the single gate driver, for the perfect choice for this module. So for sure, you can also use, let's say, a dual gate driver to control it. And there you can also get out like 0.1%, 0.2% in this range of better switching behavior. But in the end, it's only really a tiny increase of performance on the module. And that's again, it's really nice to use the single gate driver, and also Infineon offers that gate drivers, as I also already pointed out, to drive that. And with the single gate driver, you can also take advantage that the Hyperpack drives efficiency and reliability. You don't have to worry about complex configurations, right? As you usually need to do with a dual gate driver or any adjustments. So if you go for a single gate driver, you're sure you have the 100% end of line testing of Infineon, and you also be sure that it's really perform flawlessly.
Are there any other special requirements for control in terms of the microcontroller?
Not to my knowledge so far. Let's say it's a Hyperpack Drive plug and play module which you just can take, and this makes life real easy for the tier one and the OEM to use that module in combination with that or existing gate driver which they already have. Could also be a possibility, and that's pretty simple. It's a really simple approach.
Okay. So getting into just sort of where this is targeted at, and I'm sensing the answer is going to be where Infineon's existing modules apply, but can you get into sort of how and where the new Fusion module will be used in EVs?
So, well, the Hyperpack Drive Fusion power module, they are going to establish a new power module standard for the traction inverters, I would say, in the e-mobility sector. These modules are specifically designed for electrical powertrains and inverter applications in electrical vehicles, where high power density and efficiency are crucial. They are perfect for the modern electric cars, for the EVs, and that require both the high power and a compact installation. The modular design of the Hyperpack Drive makes it very easy to integrate them into different vehicle types and also the platforms, and also giving the car manufacturers and the tier one their flexibility which they need, right? So we can expect to see these modules being used in a wide range of EV applications in the near future. Let's say from compact city cars to high performance cars.
All right. Well, Andreas, thanks so much for taking the time to do this and walk us through the new technology.